We still in?
Yeah, works.
All right. Shall I just start then?
Yep.
Cool. So yeah, this is the paper. Some of you might have read it already. Peter just said that he definitely has read it a long time ago, and it's a fairly old paper as well. It's from 2014, so the date here is not correct. How did I find this paper or got inspired for this talk? In my hilarious quest to solve rock, paper, scissors with deep learning, I came across this book. And this book is actually a very good introduction to deep reinforcement learning. And it talks a bit about the history, about how deep reinforcement learning came about, what sort of struggles where people overcame with. And that sort of, inspired this paper club, really. What do they do? Well, on a surface level, what they're trying to do is solve Atari games, which, there exist environments on your computer that you can emulate these games, where you can sort of pretend playing without actually really playing the full game. And the idea is that you let an algorithm run and it learns playing the right actions at the right time to beat the high score. How does it look in practice? So what is reinforcement learning on a more abstract level? So typically you have a state space, and just say it's a finite state space, even though it might be infinite, but you can always sort of assume it's finite. And we have a finite action space so that at any state that is possible, we have a finite number of actions available that we can use. And if we are in a state and we do an action, we get a reward for it. No rewards is also possible, so we don't always get feedback. And afterwards, depending on the action we took, we get transported to a new state. And the new state might be terminal, or it might be just another state in our state space. And we repeat the same again. We have actions available and so on and so forth. These games we are talking about tend to be episodic, meaning that there's a finite time after which the game is over. And what is also quite important is that the reward and transition functions often are stochastic. So you do the same thing, you don't always get the same outputs, which is, I think, quite common in a lot of games if you think about it. What is the overall goal of reinforcement learning? Well, it's policy finding. A policy is a policy, or sometimes it's called strategy in game theory, is a function that takes any element of your state space and assigns typically a probability distribution over the actions that you should take. And in these sort of games, which are essentially single-player games, right? The optimum action should be, one action should have like a 1 in probability, the rest 0. But the policy along the way tends to be mixed, so to speak. And what we're trying to maximize is the episodic return, is essentially the weighted average of the returns based on some decay factor, so that we're trying to discourage just taking the one action that gives me the best reward now, if in the future I might maneuver myself into a position where I'm not getting many rewards anymore. And that whole setting is called a markov decision process, meaning that it's really one person versus an environment, essentially. Is it difficult? Well, at this point, or for some years, you could argue that classic reinforcement learning has been solved. There are algorithms that tend to work, and you can prove that they work. One approach is to define a value function, which is the expected value of your reward, and this reward function is already the one that has the takes the future rewards into account. And we're trying to optimize this expectation for all the possible policies or strategies that we can have. And once we have such a action value function, right, we can we also have an optimal policy, right, because it depends on it's already maximized. And once we have these values, we can, for any state, say, okay, we just take the action that maximizes my value. And if I follow this, then I have also the optimal policy. So it's a sort of closed definition, if you will. And one key to solving this is to realize that there's a sort of consistency equation is being fulfilled, that the best action I can take now depends on what best action I can take in the next step. So the current value should be the expectation of the reward I get plus the discounted optimum reward I can get in the next state, depending on which state I'm getting to, of course, in the next state. And this equation, called the Bellman equation, tends to be the centerpiece of all approaches that sort of try to optimize and find this value function.
Arvid, there's a question in the chat, which is, what is the expectation over in these equations?
Good question. It's essentially overruns. If I were to start, given the same state over and over, given the same state and the same action at this point, and let it run to the end of the run, what would happen, right? So we sort of assume here that all the history and Markovness is already captured in that state, whatever that state might be. Did that make sense?
Yeah, I would add to it that the reason why there's an expectation is because the environment is stochastic.
Yes.
So you could perform one action and get multiple different results, and there's I think a big T in the second equation, which is there's usually like a transition model which tells you the probability of going to the next state given an action in the current state. And that's what in the second equation you're taking the expectation over.
Yeah, exactly that. Your reward itself is a distribution, and the next state you're getting to is also distribution. And as Peter said, in principle this can be easily extended to infinite times, but then of course the discount factor has to be smaller than 1, and you need a reward function that's reasonably well behaved and everything. But most of these Atari games are finite. There is an end to it, and be it just you run out of life points or whatnot. Right. Any other questions?
Nothing in the chat right now.
Cool. One way to solve this. Yeah, please.
Arvid, sorry, I had a quick question because I was reading the paper, and one thing that interested me was the fact that the state is the state as they define here is basically all of a sequence of previous states and actions, right? And they say that
finite series. It's 4 frames they take. Yes.
Oh, okay. I was confused why that matters. Like,
we're going to get to this in a moment, but it matters because things like momentum might be important, right? So imagine you're watching a bullet on the screen in some Atari game. It probably matters whether the bullet goes left to right or right to left. And from a single frame, you wouldn't see it. But if I know the previous frames, I know whether the bullet is moving in one direction or the other, and so I can maybe dodge it. And so that becomes my state, right? So in physics, your state is not just where you are, but also which speed you're moving at, or which momentum, which I think, interestingly enough, we're going to talk about next week in Peter's paper. That make sense?
See.
Cool. One way to solve this is, for example, with Sartre 0, where we observe transitions and we update our estimates of the next of the current state by, actually this is probably should be an A prime here, by essentially updating our current best value estimate based on the reward that we're getting and the state we're gonna go next to and the action we take there. And if we do this over and over, this works. And what I think is absolutely marvelous is it's model free, right? We don't need to particularly model the dynamics of the environment. We don't have to explicitly model the dynamics of the reward. We just care about these averages, and it still provably works. That doesn't mean that modeling your environment doesn't help. It can make things in a lot of cases a lot easier, but it's strictly not necessary. And the rest of the paper, all we do is talk about this model-free approach, where we just observe rewards, transition states, and learn from that alone. Typically, the rewards are sparse. That's why we take the next value of our Q function here, and that is called bootstrapping. In principle, what you could do is you could always simulate to the very end and then put your final reward in. That can be a bit problematic because there's high variance in there, and it's not necessarily very sample efficient. But if you think about, you do a good move, you move into a state that is very valuable, but by pure random chance you don't get a reward for it, then you probably should get rewarded at least a little bit anyways, just because you did the right thing and maybe you found a new way of getting reliably into a state that is actually beneficial. So this idea of using the expected value of your next state is quite beneficial in a lot of reinforcement learning algorithms. Yeah, the problem is it's a trade-off, right? You're not getting anything for free, but what you do is you introduce bias. If I am bad at estimating the value of the state I'm going to, then this error also comes to your current state, and that is so there's no free lunch. Then another thing that is there is that it is typically an off-policy learning. So actually, what we typically want is we're trying to find the maximum value of the next state, right? That we're using. And that means that a very greedy policy that we would be running here would always maximize, but that would probably freeze into a state too early. And what we actually want is we want a policy that explores at least for some time a little bit. Now, how could that look like? It could look like such a case that every 10th action or like there's 10% chance we take a random step. And if you think about how that might affect the outcome of the algorithm, well, the policy that you train, the optimal policy will change. A great example of this is this cliff problem. The agent starts at the state S and tries to go the fastest it can to state G. And the fastest way is, of course, walking in a straight line from S to G along the cliff. The problem is in this formulation that if you walk off the cliff, you get a very, very large negative reward. So you get heavily penalized. And now assume that you have a policy that is random every now and then. What is the optimum policy to behave in, or the optimum action to use in such a situation? When you start out, the algorithm learns to actually walk inland a little bit and walk away from the cliff, but then walk horizontally and then come back to the final state. This makes sense, right? Because if you do a random walk a little bit every 10th action or so, you would walk potentially towards the cliff, and instead of losing, you still have enough space to come back again. And this, on average, will maximize your reward. However, that is not the best policy you can do, because if you really want to optimize it, you take the exploration off and you go in a straight line. And this idea of learning optimum behavior from a policy that is not the same that you use for training is called off-policy training. And it will look different. Now, and the question, of course, also came up already with Gerard's question, what is a state in an Atari game? But in this particular case, it's frames and actually concatenation of frames. So the frame is a full image, and concatenation of them is a very, very highly dimensional object. So it is nearly impossible to actually count all the states. So we have a lot of different ways to have the pixels arranged on the screen. And so that means that the number of Q values you would have to update in our SARS algorithm becomes massive, and no memory on Earth can hold these for sufficiently large games.
Arvid, there's another question.
Yeah.
So in practice, how would you make it work so it's realistic, i.e. walking a valid path while not falling off the cliff instead of following invalid paths or flying? So basically constrain the agent based on the environment.
That is of course when you create this source algorithm, you have always a policy of how you go about exploring, right? So you take your best policy and sometimes just deviate from it. In practice, you would actually change this to maximum here, and you can look at your past behavior and try to get the best estimate of your Q function if you were to use this greedy policy. Then it should in principle come to the optimal path.
I'll just add to that so in video games and in a lot of traditional RL stuff, you're assuming that you can start again from the beginning. So you could die and start from the beginning. So a lot of policy, a lot of these methods will just let the player fall off the cliff and then restart, and you'll see you got no reward for doing that, or maybe a negative reward.
Yep.
But then there's an entire branch of RL called safety aware RL, where you might be exploring an environment where you can't fall off the cliff. And so there's a completely different, there's a lot of literature around that, where you have to be aware of safety when you're exploring as well.
Yeah. But this feature of learning optimal behavior from training that is not perfect or has these limitations is of course quite desirable and something that we do want, right? And yeah, coming back to the input space. So the input space is huge. So we have no real chance of actually enumerating all the possible states. So what we instead want is a functional approximator. So we have a function, and in this particular case, it's going to be a neural network, but it doesn't have to be a neural network, that is parameterized and that can learn the value action. So at each state, what is the value we would assign to a given action? Now it turns out if we have these three combinations of features, function approximation, because the state space is so large, bootstrapping, because we want something to be efficient, and off-policy training, because we want to learn something without sacrificing exploration. If you combine these three things together, it turns out this can become unstable. And it's called the deadly triad. And that was one of the big obstacles, maybe in the early 2000s, of where it was not sure whether reinforcement learning will ever be able to solve these big problems where you have function approximation, where you have input features like screenshots in an Atari games that are perhaps too big to enumerate. Now, why could this become unstable? There's a great counter example of where such a system becomes divergent, and that is I can't pronounce the name, Stiglitz and Van Roy counter example, but it goes back to an idea by Sutton. And the setup is we have a very small problem. It's not even an action problem. What we're trying to do is we're trying to value the situation by itself. So we have two states. Each state has only one feature. And in the first state, the feature has a value of 1. In the second state, the feature has a value of 2. And we want to learn a linear value function that essentially size of the feature times some omega that tells us how valuable is the state. In this particular problem, we can go, we start always at this state, move to the next one, have a chance to move back based on epsilon, and eventually come to a terminal state. Now, the problem is we're trying to find the value of this, of ending up in this state. And you could think of it as, say you have a bigger game where you have maybe one action is for you to get into this state, and you want to know what is the value of doing such an action. And the answer is quite obvious, right? Because at no point do we actually get a reward. We just move through the system, perhaps go a couple of rounds about in here and go to our terminal state. We never get any reward. So the actual value function, the correct value function should be 0. And so omega should be 0. And even though this is a very contrived small system, the linear model is able to represent the correct answer, namely 0. Right? So so now let's assume we have a system that tries to train it. We start with any omega value as a starting point. We play an episode and try to update our beliefs about what is the value of each of these states. Now, if we do this, we get this equation, right? So we're trying to find in step K the optimum omega that minimizes our expected value versus the value we get from our reinforcement target, which is the reward of function, which is at any point reward of a state, which is at any point 0, plus this decayed value of the next state. And if we plug the value in, we see, of course, the reward for the first function is 2 gamma times the reward of the next state, or gamma times the reward of the next state, which is 2 omega. And the value of the second state is then the option of cycling back, getting rewarded again, and the sum of those two. And of course we can, because it's just the sum of 2 squares, we can find actually the minimum omega k value for this. We get this equation where we essentially take whatever previous estimate we had of omega k minus 1 and multiply it with this factor 6 minus 4 epsilon over 5 times gamma. And for the Keynight, it can be seen that if gamma is large enough, essentially for any epsilon really, we get a divergence where our prefactor might be larger than 1. So if we start with a omega that is larger than 0, after each step we get another omega that is larger than 0, but it is multiplied by factor larger than 1, so it gets bigger and bigger and bigger. And the same if you start with a negative omega. And essentially what happens here is that at no point do we get a reward, but we sort of reward ourselves by choosing our value approximation, right? Our value approximation becomes our leading factor in our reward, and so we end up going in circles, reward ourselves without ever having obtained an actual reward of the system. It's more like a promise of a reward, and that is unstable. And so that was why people thought that, or why it became clear that you can't prove that function approximation and bootstrapping and work together. And so people were not sure whether we can ever learn these big problems. However, there were some early breakthroughs in games like TD Gammon. So TD Gammon is an algorithm that they use to train backgammon to superhuman level, I think. And so there were some early signs that there might be a way around that. Sorry, that was probably very, very fast and convoluted. Are there other questions at this point?
No questions in the chat. No questions for me.
Right. So now this is where this particular paper comes in. So what did they try to do in order to solve this problem that there are this self-looping behavior that causes these divergences? And the big idea is to use a replay buffer where you store the transitions between the states, and you create a large data set, and it's a finite size data set. In practice, I think it's like 1 million states, and whenever a new sample comes in, an old one falls out. And during training, we sample randomly from these states. If you look closely, we don't store any model information here. So we don't store any Q value information, and we sample just these transitions and evaluate on those and try to retrain our algorithm. And it had several benefits. For once, we reuse the same experience many times, and that is clearly a thing that it improves our sample efficiency, right? If our model updates, our valuation of different states might changes, so it might be good to go back to old cases and review whether you learn something new about them. because in reinforcement learning, you get samples close together, and they are not necessarily independent, right? If you think about Super Mario, so you run through a level, and the samples that come in close relation to each other, they tend to be from the same part of the level, or in Sequester, so it might be the same side of the screen. So that is something that certainly encourages this feedback loop behavior. But by using a replay buffer, you sort of suppress it a little bit, because you have a just as likely chance to sample older experiences that are not from there, and so you would expect that the thing that the model sees when it trains is going to be more varied than just the recent experiences. And because Q, our estimate of Q is not part of the replay experience, we essentially are allowed to forget bad decisions about our cues, and so that again suppresses these feedback loops. Yeah, and so in practice, yeah, we have about 1 million last experiences, and we sample uniformly. You could think of that this might not be perfect either, that there's probably a smarter way of going about it, but maybe we get to this in a moment. So that is the algorithm. You have a number of episodes, and in each episode you essentially play the game. You play greedily with a chance epsilon to select a random action. You reprocess your images, and these are being stored, and the emulator just keeps running. And I'm slightly confused. I think they do the gradient step at every time step. I would almost think that this step where you sample from your mini batches from your replay buffer is probably outside of this inner loop, but I might be wrong. And the action that is being, or the loss that is being calculated depends on the rewards that are being sampled and the maximum value of a network. In practice, that network is actually being frozen. So you train your network, you freeze it, and then for the next couple of iterations, you don't change that network, you use another network that is being updated. So that is why when you try to minimize the distance between this target and the output of your Q network, you only differentiate once and not twice. And that actually turned out to be also make it a lot more stable, because then your network, your target network, tends to be trained on old values rather than just the recent values, which again suppresses these feedback loops. And some more of the practical things. So the images are all the same format, 210 by 160 pixels, and they are in color. What they ended up doing is reduce it down and grayscale it. And actually, in this particular case, they also cut down the image further to, I think, easier load it to GPU. But yeah, there's a question.
Yeah, just a quick question on the last slide. So they were taking gradients with respect to the target network. Is that what you were saying before?
So that we have two networks. One is the online network, which is the one that is currently generating the samples that generates the current action values, and this is also the one that's being updated. But if we want to update that model, we have to calculate the actual values of the states that have been reached in those transitions. And for that, we could use the same network, but actually we use a network that has been frozen, so that when we take the squared difference between the value of the targets and the current network, we only differentiate with respect to one and not the other, so that the targets sort of are fixed.
And that avoids the feedback loops.
It does a little bit. At least the recent feed, because Q hat, so the target network, does not know about the recent experiences, because all the recent experiences are closer correlated. It it can be problematic. And by freezing it and only updating the target network every couple of iterations, we break that relationship a little bit.
When you say update, do you just say like, okay, I've updated it for 5 steps. Now the target network is the new network, is the network that I've updated. Okay.
Exactly. I think Q, they didn't really say it here, but I think at some point Q will say that they start out the same. Over a couple of steps, Q will be allowed to move to a new network, and at some point it becomes a new Q head, and you start again from the same networks, and let one update every couple of steps, the other one is being frozen, and then you swap them out again.
Cool, thanks.
Any other questions? Cool.
Oh, I think there was one, but you answered it.
All right. Yeah, so they cut down the images, make them grayscale, make them smaller, and take 4 images together. And they also scale the reward. So whenever there was a positive reward, they just assign it a 1, -1 for negative reward, and for 0 if there was no reward. This has a benefit that you can use the same learning rate across all games. However, you sort of lose something in the process, right? Because certain actions that create double the reward, they would be evaluated the same as an action that does only 1 reward unit. How does the architecture look like? It's actually very, very simple. One of the big choices being made was that the Q outputs is the end of the network, essentially. That an alternative approach would be to have your state and have the action as an input to your network, and the output of the network would be with respect to the input of what action you're actually looking at. But what they do is that because the number of actions for each game is the same, within a game the number of actions is the same. So you just have an output head that has a size of the number of actions, and so at each point when you run through your network once, you get the value for all 4, 5, 8 actions of that game. It's the same architecture for all the games, which is quite great, because if you think about how many different games they were looking at, it's like Pong and Sequest, which are very different games, but everything else was the same. We have 2 layers of convolution and relative nonlinearities in them, then essentially a dense network, and finally the head that maps it to the number of actions. So the only thing that really changes between the different games when it comes to the architecture is the size of the final head of how many actions we're trying to find a value for. Apart from that, it's all the same. And they run it with ARM as prop, small mini batches. They start with a very high rate of randomness at the beginning, where essentially any action is random, but over time the randomness goes down. But in the final state, so after 1 million iterations, it would still stay at 10% random. So any action is being taken, the 10% chance this action would have been random. They train on. Yep. Another question?
I can go second, because I think 2 people raised their hand.
Okay.
Who else raised their hand? Or is it just me? Yeah, I guess it's just me. So this is something that's confused me a little bit. It's like it's an off-policy approach, but you're doing epsilon greedy, where greedy is determined by your value function, right? That, like the one you're learning.
Yes. No, epsilon is not depending on your value function.
No, not epsilon, just the greedy part. So like, how do you choose what action is the greedy action?
Yes.
You're using, so I can understand the epsilon part making it off policy, but I was thinking like, this must violate it in some way, because you are using the policy to choose actions for exploration. I don't know.
Yeah. I'm not sure what to answer. I mean, you would hope that because the action space is quite large, right? That you still get to states that you can value. So you would still be able to update your value function based on the transitions you only have, right? So you would expect that that you would lose not too much about it, and that because you only update the actual actions you took, and because you only take the next reward and then the Q factor, you sort of, I don't think you care too much about when actions that come even further down the line and that might be random, because these shouldn't affect how you evaluate your current state.
And then there was a question in the chat, which is, does 1 million iterations equal steps across episodes?
I would think sorry, what was hang on 1 million frames, right? So I don't know whether one frame would be here. I think one frame is essentially one run of the emulator. The number of episodes will then depend on the game being played, right? So certain games you probably have more frames until you reach the end than others, but I don't know the answer for sure.
Yes, it's quite interesting, right? Because then different games, they train by frames, not number of episodes. So potentially, like one game they play only n times, another game they play much more to get to the 10 million frames.
Yeah, that's correct. And I think we're going to see some of those results also in the evaluations. They actually, it was also quite interesting because the emulator runs a lot faster than their network. What they would be doing to be more efficient is to run, sample the action that you take, be it greedy or epsilon, and use the same action for the next 4 time steps, which probably is fair because the sampling rate of the game is high anyways. And if you think about human reaction times, when we press the button, we probably also smear our actions out a little bit. That was working fine, except for Space Invaders, because if you then take only every 3rd frame, you get a problem with aliasing where lasers, which only show every X frame or so, essentially become invisible. And so for Space Invaders in particular, they had to choose a different number of time steps.
I wonder how they figured that out. I wonder if it was just like, why is it doing so bad on Space Invaders? And then they had to look at it or something.
Probably the intern had a hard day and had to actually look at this stuff, more or less look at the data by hand. Yeah. How did they evaluate? Well, naturally, you'd say after one way to evaluate how good you're doing is that after a number of training episodes, you freeze your network, you let it play completely greedily rather than just explorative, and measure what the reward outcome is. The problem with that is, and you see it in 2 games on the left, is that it's very, very noisy. So even if you train a lot, you still get noise in your outputs. So that is perhaps not ideal. What they suggest is to use the estimates or the average of your value function or Q functions to suggest how much value the algorithm or the trained network thinks it has in the game. And you would expect as it learns more, it assigns higher maximum value to it. And you could argue that this is also a indicator of how much you have trained. And the point is that even after, say, 100 episodes, your model still seems to be improving in the maximum value it attaches to a particular game. Yeah. That how does it look in practice? So say you play a game, do you see in the values what happens in the game? Here's an example of sequest. On the left is here's 30 frames, and I think it's the maximum Q value, or the average Q value for those games. You see here, there's a very sharp increase in the Q value. What happens? Your submarine is here, and on the left is a fish or something coming into the screen, and the network thinks, oh, this is something we can possibly exploit. Just short time later at frame B, what happened was that the submarine was shooting a torpedo. The torpedo is about to hit, so the algorithm already assigns large value to the event because it knows that it should get a reward anytime now when the torpedo hits. Once the fish is dead, the Q function drops again because there's no target in sight anymore. And so you can sort of see that the algorithm has learned from the raw images salient information that allows it to evaluate the next couple of steps. They compared it across other reinforcement learning algorithms and against humans. So for a human, I think they had a human play for 2 hours, or several human play for 2 hours, and then take their median scores and take them as baseline. What also was quite interesting is that they said in another paper that did a similar approach, the humans were a lot better in this DeepMind paper, which seems to suggest almost that in another paper they made the human scores lower, so it just looks like they would be getting closer to human-like performance. But here they show that, first of all, that this DeepQ network is a lot better than other reinforcement learning approaches across several games, which is already a big success, right? And in some games like Breakout, they're even better than humans. And they also compare against an evolutionary algorithm, and they do rather well there, despite the evolutionary algorithm on the SARSA approach they took here, using handcrafted features, which has, of course, the benefit of having some expert input. And even without that, DQN is beating them quite handsomely in some cases, which is great. However, compared against human level performance, it tends to be pretty well on some games, but a lot worse on others. And those are the ones that have the larger time frames, like Qbert and sequest, where there could be either you have to have more forward-looking approaches in order to get better at the game, or as Gerard suggested, that maybe the amount of training that has been used was effectively less episodes, just because there are more frames in one effective episode of play. But again, it's a huge success, in particular because it shows for the first time that there exist generic algorithms that can actually overcome this deadly triad problem, that you can achieve superhuman performance without having mathematically provable algorithms that always work, and just by essentially using this replay buffer, which is great, and a very generic algorithm as well, which is cool. How much time do we have left? We have a couple more minutes.
Yeah, 10 minutes.
Yeah, there. Of course, the story doesn't quite end here. There's another paper, and originally it was planned to be 2 journal clubs, but they sort of compressed it. That they made a number of improvements, and in a follow-up paper in 2017, they compared 6 improvements that you can use that are all independent of each other, and each of them improves the baseline a bit. So the baseline here would be DQN, the model we just talked about would be down here. And they have these 6 improvements that either came up themselves or took from other papers, and showed that you can combine them to get essentially something that is a lot more efficient than this network we were just talking about. And it's called the rainbow paper, because they called it rainbow, also because it took rainbow colors on the graphs. And if we have a little bit of time, we can talk about what these improvements are, because it's quite interesting. The first one is WQ learning. One problem of this reinforcement learning is, and that is something that's also seen in classical reinforcement learning, is that if we have a bias in the error, right? We choose on the one hand an action where we think it is the best action, and based on a approximation of a value function. So if there's an error, we actually get punished twice, because for one, we choose the wrong action, but then also we use the value of that action, which is already high biased, because otherwise we wouldn't have chosen it, and put it into our algorithm. So one way to overcome this is to take two networks, one to choose the action, the other to assign the value to it. And so if one is high, the other one statistically will not be high so much so that it roughly cancels and becomes unbiased. And if you see here, oops, that is the DDQ network. This already leads to massive improvement in the efficiency of your reinforcement training, which is great. So we have two updates: one for the target, one for the choosing of the action, one for the target function of the action, and you just swap around between the two. Another thing, we talked about how in the replay memory we essentially sample uniformly. And one way to make this better is to sample based on what was the last error that when we are training this particular on this particular data point, what was the last error we had there, and sample proportionally. That means that we see samples that we struggled with more often in our training, and can learn from them more. It makes sense. So there's this additional parameter W, which is, if you set it to 0, means uniform sampling again. But if we make it higher, we look at samples where we had a problem. Now, of course, now we have to store some values of our model as well. So these differences we have to store alongside our replay memory, but it's not a big difference, and also shows massive improvements. The next idea is dueling networks. Essentially, what it means is you split your network into two outputs. One is the value function, and another is the advantage function. The idea being that in certain states, no matter what action you take, they all look good, and some just look slightly better than others. And if you have a way to estimate the value of a state, you can take the advantage, which is the difference between the value of a particular action and the average value of that state. And so essentially what happens is you stabilize your targets, that the two actions that both look good get essentially added more difference to them, because one is measured as relatively better than the other, rather than they're both being relatively good compared to some arbitrary baseline. And that stabilizes the network, makes it a lot more efficient, especially when you have more actions available. So for a game with 5 or 10 actions, it's barely beneficial. But if you have a game with 50 or 100 actions, that is, of course, in practice quite a useful thing to have. These become a lot more stable. And exactly, and because here also that one benefit is that whenever you measure an action, that the value function always gets updated. Whereas in the past, of course, if you use an action, only one of the Q values would be updated. Multi-step learning is relatively simple. That rather than just taking the next reward, you take, say, the next 3 rewards, and only then move to the target network for your value approximation. And so you have a bit more noisier term here, but you make less use of your approximation, if you will. Distributional reinforcement learning. So that is a really interesting paper behind that. The idea is, rather than training your value function, what you actually learn is a distribution of values. You take your output rewards. They don't have to be -1 and 1 anymore, but rather can be from a range. And they call it atoms. So essentially, you would take your output, say, of your score, whatever it is, and chop it up into, say, 51 pieces. And 51 because they did it here. And then you train a classifier to predict what is the weight of each of these output components. And interesting enough, if you know you go to your next state, you can still choose an action greedily because you can predict for each action you take what is the distribution of the rewards. You can take whichever action has the highest mean value of the distribution, which would be your Q value. And you can take those distributions of your next state action and shift them forward, similar to a Bellman-like equation where you take whatever is your next state, you take the distribution, you multiply it by gamma, and add your reward. You get a new distribution for your new state. You have to do some mapping and projecting, so it's not quite as simple as it looks. But then your reinforcement learning problem, which was typically a single squared error minimization, now becomes a minimization of a KL divergence or a multi-class prediction, if you will. And that seems to stabilize things a lot, because if I see a reward that is perhaps only rarely appearing, it updates of course this KL divergence differently than if it was just the mean. And so you can still learn from it, but it doesn't throw things too much off balance either. And so that is also a very, very interesting paper, but very mathematical, but yeah, quite interesting in and of itself. And also you can use it for the target replay sampling. You can just sample by this KL divergence as well. And last improvement was this noisy nets. The idea is that for certain games, you need a number of good actions in a row in order to progress to a state you haven't seen yet. Think of Super Mario, where you have to have fairly reliable inputs, otherwise you die too early. And that can make playing the game inefficient, right? If you play every 10th action randomly, then states where you need a high degree of perfection in order to get there, it becomes fairly rare to reach them. But the idea here is to add noisy layers that have a non-noisy component and so the linear layers with the non-noisy component and the noisy component. And so there are noisy weights in there that are multiplied by essentially random numbers. And as the model plays, it learns that it doesn't need those. So over time, it will put the bias of these noisy terms to 0. And for certain states, but it's of course state dependent, for certain states, it will have less noisy outputs than others. So it sort of adapts its exploration rate by itself. And that seems to have also stabilizing effect, and essentially means the model gets earlier to states in the system or in the game that require a certain finesse to get there. And if you compare all of them together, you get this massive benefit where you, for a large number of games, so they tried it on 57 games, they optimized, I think, the parameters for 3 games individually. So they took one change, say the distributional case, optimized the parameter on 3 games, and then didn't touch it at all. They combined all of their changes into one. They didn't change any of the hyperparameters, so they essentially trained 57 times on 57 different games with the same set of hyperparameters and get massive performance boost, which is crazy. And you get a lot more games where you reach superhuman scores, and also these games that have longer horizons, like Sequest, so they ended up beating to a much higher level. And yeah, that concludes the talk. So it shows. I mean, this is a seminal paper, right? Not because playing Atari games is fantastically important, but more because it really shows that this deadly trait can be overcome, and it really opened up the realm of deep reinforcement learning for practical applications. And that it's a very powerful combination to have this function approximation, bootstrapping, and off-policy training, because you really can push the boundaries of what your past data could give you without reinforcement learning. And the idea was that this experience buffer is the thing that stabilizes and thereby avoids a lot of the problems that come from this feedback loops that you would have in traditional deep learning. And there are many ways you can go about to improve the performance of these algorithms. And so it's, if anything, became a bigger field rather than a solved field, which makes it exciting for research even now. Yep, that's it. Any questions?
Yeah, I had a question about the rewards. So,
Yeah.
You mentioned that they flip the rewards to +1, -1.
In the deep Q paper, yes. In the later paper, not so much, right? Because there you have these. One of the changes was to have this distribution. But yeah.
Yeah, but in this paper, I'm just surprised that works. So effectively, it's like doesn't matter whether the reward's massive or small. It's just +1 or -1.
I suppose so. Yeah. Yeah, Dwayne, very good question. So not quite sure what you mean by stationary, but there is this thing where there is a concern that a algorithm essentially memorizes the best behavior. Like in Super Mario is one of those games where I think you always start from the same, and there is no real randomness. So they didn't do that in the Deep Q paper, but in the Rainbow paper, they evaluated the algorithm on random starts. So you have a human play the game for a little while, and then they stop and essentially hand it over to the algorithm, and thereby you essentially remove that the start is always at the same point, but you start from a reasonable position, and typically, yes, the algorithm quality drops across many algorithms, but you still get superhuman performance from that as well. So it shows there is a certain element of stability to it. Yeah. Anything else? I mean, the question is whether it's the data itself that is problematic. Is maybe too simplistic because it's 2D rather than 3D. I would argue that by itself is not a fundamental difference, right? It just means that the course of dimensionality is even more severe, but the it's stacked frames of anything, right? You could take any dimensionality and squeeze it into a dimension that into a shape and stack it. So the intrinsic dimensionality of the game, I don't think is that important. And they have solved games that are definitely more complicated, like StarCraft, I think, though I don't know any of the details. So there might be caveats to that as well. But I think that the point of the triad is that function approximation fundamentally can work. I think that is the big thing. That how good the function approximation is of course another question.
Great. I think we'll end it there. But thanks, Arvid, for the talk. It was really good.
Yeah.
And thanks everyone for coming.
Thank you very much for listening. Bye-bye.
Thanks, Arvid.
Have a good weekend, everyone.
You too. Thanks. Bye.